तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In last class, we had a glimpse of a technique that is very useful for solving nonlinear problems, and you remember that we call this as an incremental iterative approach. We said that Newton-Raphson scheme, which we ultimately derived an equation also, was one of the techniques for implementing this incremental iterative scheme. Let us do a small problem to understand what the scheme looks like, but even before we do it, let us understand the whole technique through a graphical presentation. Now, in other words, if you look at, say for example, a load deflection curve, a nonlinear load deflection curve, say deflection the x axis, and essentially this is a nonlinear curve. So let us say that it goes on like this, right. Now, our whole idea in a one dimensional problem, though strictly for one dimensional problem, it becomes slightly more complex when you go to multidimensional problem, is to actually trace this curve closely. So, in other words, the whole idea here is, given a p, how do I find out a displacement corresponding to this p, so that the load deflection curve automatically says that whatever is the internal forces, stresses, okay, which generate internal force, equilibrates this p. Is that right? So, what is that we essentially do? If this is the total p that I apply, p total that I apply, I divide this into smaller incremental loads, okay, say p1, p2 and so on, okay, until I reach the total load to be p total. Now, let us understand how this process of Newton-Raphson scheme is applied to a particular nth step as we move from nth step to say n plus 1 step. Okay. So, let us say that that is the nth step. So, I have a load of Pn, clear, and I have to get to equilibrium step to Pn plus 1. Do not tell me that I can just get this point and do it, because I do not know this curve. I am trying to get this curve, I am trying to trace this curve. So, it is not that Pn plus 1 I know it, just go there, that is not the issue. Okay. I am at Pn, I know everything about point Pn, I do not know Pn plus 1. It is only an illustration that I put this. Okay. So, let me draw that in a more, I would say, detailed fashion, zoom into this portion, okay, and see what I do here, right. So, I am there like that, and that is Pn, okay. I have to go to Pn plus 1, okay, or rather just a second, let me put it as Fn. I think last time I used, so that there is no confusion, let me put it as Fn plus 1, though usually P is used for load. Let me say Fn and Fn plus 1. So, that will be clearer, because I think that is what we used last time. Now, so I know Fn, and what are the other things I know? I know how to calculate the tangent stiffness Kt at this point. I know how to calculate the tangent stiffness Kt at this point. So, tangent stiffness is nothing but, what is it? Dou p by dou u, okay, in which case, in this case, it happens to be nothing but the slope of this curve. Okay. So, the initial slope of the curve at the start of my iterations or at the beginning of my journey towards n plus 1 is very well known. Okay. So, that is the slope of the curve. Let me call this as say kt, okay, and usually iterations are given here at the first iteration level. I know that, right. Now, when I start this iteration, what is the error? The error is, that is my error, okay, because my internal forces have now equilibrated up to Fn. My internal forces, if you remember, we had called this as Pn. Now, at that point of time when I start my journey towards n plus 1, what I know is sigma n, and that sigma n gives rise to Pn. Okay. So, if I now calculate the internal forces at that point of time, what I will get is Pn. And my error, if I remember, and if you remember, that it was the difference between the load that is applied and what you have got internally. So, Fn plus 1 minus Pn, right. So, that is the error. So, that would form the right hand side of my expression kt into delta u is equal to psi, right hand side of my expression for my first iteration. Is that clear? Okay. Now, that means that I will solve this equation kt into delta u, okay, is equal to, or du is equal to psi. So, I will get to a new d, okay, or new u, let me call that as du, okay, du at the end of my first iteration, right. Okay. Now, so that means I am here. So, I calculate now epsilon, right. With this we will see the details in a minute. I calculate epsilon, and from epsilon I calculate sigma. Et into epsilon is equal to sigma. How do I do that? Note that d sigma by d epsilon is written as Et, and I know how to calculate d sigma by d epsilon, that is given. We will see an example in a minute. So, I know it. So, I can calculate d sigma, in other words I can calculate sigma. So, knowing displacement I can calculate sigma, okay. Knowing sigma I can calculate the internal forces, okay. Or in other words, I will go to, this is the point that is given for this displacement, the force, the internal force is given by the point lying in the load deflection curve. So, if this were to be the deflection, this will be the load, that is what it means. So, this will be my new internal forces.
So,
yes.
last time we had the error is equal to load at n plus 1 iteration minus the internal force at the n plus 1 iteration.
Yes. So, we had, in other words, the question is, what is the error now?
No, because error, last time you told that error was error in the n plus 1 iteration is equal to load at n plus 1 iteration minus
Yes,
load at n plus
correct. So, in last time we said that the error is to be calculated at the end of first iteration. I have not yet calculated the error now, okay. I have not yet calculated, okay. That is my next step. I used this error, first step error, okay, because I am at Fn. What is the error that I used, okay. We can call this as zeroth error at the start, zeroth error, okay, at the start of the increment, okay, or sorry, iteration. Is that clear? So, I used this. This is the error when I increase now my step. Is that clear? So, that is the, in other words, this error, if you want, you can call this as psi n plus 1 0, that is the start, which is equal to the error which I have to compensate, right. So, I have not yet calculated the error now. I have only calculated the internal force which is given by that point, which let me call this as say Pn plus 1, Pn plus 1 at the end of 1th iteration. okay, or Pn plus 1 if you want to write it outside also, right. Now what is the error now? Error is between Fn plus 1 and Pn plus 1, that difference. So now the error has now reduced to this. That is my error at the end of my first iteration, which I am going to use it for second iteration, okay, as the input, right. Okay. So that is my error at the end of the first iteration, psi 1, say n plus 1. You can call this also psi 2 n plus 1, I mean anyway, but as long as you understand it, it's fine. But there may be a small confusion, so that's why I'm writing it as psi 1 n plus 1, meaning that that is the error at the end of first iteration. So what do? I look at the error and see how large it is. How large it is. I'm still not happy with it. You know, it looks like the error is quite large now. So what do? I have to one more iteration. So what do? I find out again my good old friend, the tangent stiffness matrix, dou p by dou u at this point where I'm standing now, that is at this point. So what is that? That is nothing but the slope of this curve again. So I calculate the slope there.
So that is calculated at a different displacement point.
Yes, exactly. So the point is it's calculated at different displacement point, and hence the slope now will be different. That is called full Newton-Raphson method, right. So for every iteration you calculate the stiffness, what we call as tangent stiffness again. So I come to that point, I calculate, okay. So that's what I made a comment, if you remember in the last class itself. Look at the enormity of the problem. Kt in a large problem is like forming stiffness matrix. Okay, so again you form the stiffness matrix. It is again and again you are going to solve the same problem. Okay, it looks like that, and so the time required for a nonlinear problem is very high. Right, your observation is very correct that we need to calculate the stiffness matrix again. Okay, so with this error and this being the slope at that point, okay, I again calculate my better approximation for the displacement. So what do? That is my better approximation. Obviously this is the slope, if this is the height then that's the width, okay. So I will get this is the du2. So the sum of these two are, that is delta u at the end of the second increment. Is that clear? Okay. So now at that point again I calculate what is sigma and then what are the internal forces. I hit the graph now at this point. Look, I have raised this p moving closer. So again I am here. So that will be my internal forces at the end of the second iteration. Okay. So that will be called as Pn plus 1, 2. Very good. So 2. So what is my error now? Obviously this is the error. So the error has dropped. It was initially it was so much, now this much and this much. Okay, still I am not satisfied. What do? I compare this with an allowable error, which I say should be allowed, say 10 to the power of minus 6, okay, into epsilon 1. We will discuss more about that later, but right now an allowable error, which is say 10 to the power of minus 3 times, minus 4 times, or minus 6 times, which is usually used of the original error, first error. The error can't be an absolute quantity. The error that is allowed cannot be an absolute quantity, because it depends upon the units in which you are working, right. So it's very important that it is a relative quantity relative to this, right. So I see it and I am not still happy with it. I go to one more iteration and I get that point, right. So, this is my better approximation of my displacement.
What will happen if I directly apply the full load instead of going for incremental load?
Very good question. So, what would happen if I apply the full load? Only one stiffness. So, what would, let us come back to this. So, what would happen if I apply the full load? Okay. Now, this curve is a nice curve, what I have drawn. So, you will start at this point and apply the whole load here. That means that you will find out the stiffness here, okay, it will come back, stiffness here, come back, stiffness here, come back, stiffness here, and so on. This may converge, but maybe it may take more number of steps than that, but it may converge, there is good chance. But sometimes what happens is that if the curve is not so very nice, okay, the curve is say something like that, then you will not get convergence. You will not get convergence. Okay, you have to necessarily follow this curve by an incremental force approach. Is that clear? So, in other words, to answer your question, whatever be it, you can put the whole load here, do the problem, the procedure is the same. If you get convergence, you are lucky. If you don't get convergence, you have to come back and cut the steps and so on. So, this is what most softwares do. So, they put an increment, check whether there is convergence. If there is no convergence, cut down the step, okay, give smaller loads, see whether there is convergence, and then if still there is no convergence, it will cut down. So, usually many of the softwares also ask for a minimum time, what they call time step. I already said that time steps are pseudo times to carry the loads. So, what they mean by that statement that we want minimum time step, what they mean is what is the minimum load that we have to give, that is what they mean. Both of them are the same. Okay. So, you keep on cutting down the load and then you would see that things would follow the load deflection curve. So, clear? Any questions?
What is the difference between full Newton-Raphson method and?
Yeah, I am coming to that. So, what is the difference between, is there any other method for Newton-Raphson? There is, since I made a statement full Newton-Raphson method, there is also a method called modified Newton-Raphson method. There is a method called modified Newton-Raphson method. So, what is modified Newton-Raphson method? Here you do not calculate the stiffness, okay, for every iteration. You do not calculate it for every iteration. You calculate only once, maybe at the start here, and then use this itself in order to calculate further the error. Okay. So, this is an approximation. In other words, instead of using this slope at each of those steps which I have marched to get to this point, I use only the first or the initial slope.
There will be a straight line.
Yes, this will be parallel lines. See here the slope will be like this. This slope here will not be parallel to this because that slope will be different. Okay. Now, if I use a modified Newton-Raphson method, then the slope will be parallel to that. Okay. The slope here, I should not say slope, but my tangent stiffness at that point would be parallel to it. Then tangent stiffness here also would be parallel to it. Okay. Now, as it is, you can see right now, when I use the tangent stiffness at that point to be parallel to this, that is this and this are parallel, obviously the next point I am going to hit is this point instead of this point, right. So, in other words, my claim or my climb towards the correct solution is going to be slightly less or maybe more number of iterations it may take. But now, what is the advantage?
No need to calculate.
Yes. Yes, you need not calculate the tangent stiffness again and again. So, once you calculate it, Okay. You can, if you want to do whatever decomposition you want to do, you do that to solve the equations, keep it ready. So you need to keep substituting. So you have to calculate KT only once, and then decomposition you need to only do once, and so you can solve much more faster or quickly when compared to the previous case. Okay. But the compromise is that you may have to go through to a number of iterations. Is that clear? But one bit of warning, it is not necessary that this method would give rise to a convergent solution. It may also diverge. For this step, it may also diverge. Okay. There is, in other words, modified Newton-Raphson method is an excellent technique to reduce time under many circumstances, but has to also be used with a bit of a caution that your time step size also may be very small, because when you use Newton-Raphson, okay, and this depends upon the type of nonlinearity that you are dealing with. There are very many number of schemes. Modified Newton-Raphson, Newton-Raphson is one of the methods. Okay. There are many number of schemes, okay, that are used, especially when the curves are crazy. You know, they are not as good curves like this. When the curves become, or the nonlinearities become quite complex, then I can't use such schemes. I have to go for special techniques. Let's not worry about that right now, but I mean a small variant may be there. You know, you yourself can think and say, so why not I calculate the tangents every 2 iterations? Yeah, you can do that. Instead of taking the tangent only at the beginning, I can take the tangent, okay, right at the beginning, and then after 3rd iteration, 5th, and so on. That's also possible. Okay. These are gimmicks. No mathematically rigorous proofs are there. They are gimmicks to reduce the time, and if you are as long as you are able to reduce the time, well and good. Okay. So with that background, let's yes.
There is an inflection point in the field.
Yes. So that's why I said these are nice curves. So what if the curve has an inflection point? What if the curve is something? Okay, we'll get back to this curve. So they're not nice curves like this. Say the curve actually goes like that, comes in, goes like that. Okay. And what if the curve is like this, and so on? Yes. These techniques, these require special techniques many times. Okay. Newton-Raphson may not work for many of these techniques, and we will see that. Okay. If time permits in this course, we'll cover it, or at least we'll see some references where these things are taught. Okay. But these are very special circumstances where, okay, there's a snap through and so on that would happen, where solution may jump, or bifurcations and so on, and solutions may jump from one point to the other. Okay. And that gives rise to a lot of troubles. Okay. That's why I made a statement that there are special techniques when things are not as nice as what we are saying. Okay. These are, within quotes, nice nonlinearities. Okay. Nonlinearity itself is not very nice, but at least they are not that bad. They are nice nonlinearities. Okay. Fine. So before we go further, let us do a problem, and before even that, let us look at this our internal forces more carefully. Remember that I said the internal force is written as B transpose sigma, say d omega or dV. Okay. And this would call, though I am not going to give a very rigorous definition, or I am not going to do virtual work, I just want to indicate a small thing before I go further and consolidate my the whole procedure by doing a numerical problem. Okay. Now look at that B transpose sigma. This is what is called as P. Okay. So what we are interested in is what? Dou P by dou U. Of course, these are vectors P and U. Okay. So this results in a matrix Pi Uj, okay, Kij. If I call this as Ktij, the resulting differentiation, I call this as Ktij, then dou Pi dou Uj would define my Ktij and so on. Okay. We will see more details again later. Let us see what we have to do. Note that both of them are not scalars, okay, and that right now B matrix is our strain displacement matrix. Let us say it's a constant strain displacement matrix, and we do not have any other things inside it. In other words, we are looking at small deformations where my strain definition, which I had used in my earlier classes, are valid. In other words, I am right now putting a rider, understand that rider, that it is not that I can use that B which I had defined in my earlier classes, that strain displacement matrix, all the time. Okay? These are linear strain displacement. People call this as BL. This B itself may undergo changes, and B has to be written in terms of BL plus BNL. People sometimes write this as BL plus BNL. That is basically because the strain terms what you look at and strain displacement terms what you have are ones where only linear terms are considered. Nonlinear terms are not considered. Okay, so we stick to this. In other words, for small deformation, not moving into finite deformations, for small deformations, this BL is enough to define. Okay, though we may move into the nonlinear regime of stress strain curve. So let us now look at in a very simple fashion, small deformation, okay, how this can be modified. It's very simple to modify at right tangent stiffness. So this would be, okay, dou by dou u integral B transpose sigma d omega. So how would I write that? I would write this to be, so dou p by dou u, okay, to be B being, I said, independent, it is B transpose. So what would be the next term? What would be the next term? Dou sigma by dou u, but sigma is actually a function of epsilon. Epsilon is a function of u, so you can write this as dou sigma by dou epsilon into, I am just using the chain rule, d omega. Okay. So d sigma by d epsilon is nothing but the slope of the stress strain curve, d sigma by d epsilon. People call this with different names. Suppose you are working with abacus, sometimes this is called as Jacobian and so on. Okay. So this would be, or a small modification of this may be called as Jacobian. So most important, this d sigma by d epsilon is the most important quantity that is useful in nonlinear finite elements. Okay. Note that in a linear finite element, this guy straight away reduces to your well known stress strain relationship, I mean Hooke's law, and can be expressed in terms of E and nu and so on, isotropic elasticity. Right. So look at that. This becomes very simple. B transpose, of course, all of them are matrices. B transpose. Let me call this d sigma by d epsilon, say as Et or dt, however you call it. If you had called previously E, you call it as E. Previously D, you call it as D or dt. I'm going to interchangeably use because people are familiar with either E or D matrix or E matrix. So dt. Then d epsilon by du. What is this? Strain displacement matrix. So B. Okay. I've left out one of the things into, you remember in the previous case, okay, into P is multiplied, dou P by dou U is multiplied by delta U. Okay, I've just left out that term. Remember what we had for our Newton-Raphson scheme, P plus dou P by dou U into delta U. Yes, and this is what we called as, if you remember, what is that we called? This as the tangent stiffness matrix. So this is what we called as KT or tangent stiffness matrix. So what is most important in this case is that we have to have this dou sigma by dou epsilon, and this dt definition is what is important. So in fact, for any material, suppose you have new material, and if you are able to define this dou sigma by dou epsilon, d sigma by d epsilon, why I put dou sigma by dou epsilon is basically because sigma is also can also be a function of, say, the damage parameters and so on and so forth, in which case I can't write it so very nicely. Okay. It's always important that you realize what you are writing and what are the assumptions that are involved. Okay. Sometimes this sigma may be a function of, say, epsilon and, say, a damage parameter d. Then I have to extend these terms. Right now I am not assuming all that, I am just saying that sigma is function of epsilon. Most of the cases this is fine, sigma is a function of epsilon. So that is what is written as dt b du. So remember, this kt into delta u was what we called as my error terms. So that is what kt does. Right, this is clear? Okay. Maybe a few of these things we saw it in the first course itself, but it is always good to look at it more carefully and write down all the things before we start and move to further advanced material. So having said this, we will look at a small example, okay, a small derivation rather, before we move to an example. Okay. Let us look at an elastoplastic system, just a one-dimensional case to understand how things are, okay, before we move to a very concrete numerical example. So I would like that you bring your calculators for the next class so that this example can be worked out by you as we do it in the class. Okay. Now let's now look at these things for a elastoplastic system. Okay. Now I'm sure all of you know the stress strain curve quite thoroughly. Okay, a few points, okay, which I'm sure all of you remember, that the stress strain part of the elastic part, I mean, it's an exaggeration, actually it won't be so very away from the axis. Usually E's will be so very large that it will be very, very close to the axis. Now just for clarity I am drawing it like that. So this would be the stress strain curve. Most of the times, why most of the times, basically because it's easier to understand it, okay, this would also be treated as a bilinear system, or in other words, the elastic part, suppose that's the sigma y, the elastic part here may also be treated as a linear part. Okay, it's a linear part. I mean, it's possible that you treat it like this. Right. Anyway, it doesn't matter whether you treat it as a bilinear system or you treat it as a pure, okay, a linear followed by a nonlinear system. There are a few points in order if you look at the stress strain curve. Just to recapitulate that, note that, okay, when I unload from any point in the stress strain curve, okay, I have an elastic part and a plastic part. Okay. So if this is the strain from which I am unloading, okay, this is the strain from which I am unloading, then I have a recovered strain, which I call this as epsilon E, and the permanent strain, which I call as epsilon P. So epsilon E plus epsilon P. I think some of this we have done it in the previous course, it doesn't matter for continuity, let us go ahead and do it. So the first thing that I want you to understand is that these strains consist of elastic and plastic, and that the unloading is an elastic unloading. Okay. And when I reload it, obviously you know that when I reload it from here, it goes and catches the curve there. Okay. And so the yield point is now moved away from this position, which I will call as the initial yield point, okay, to the current yield point, which is at this point. So the most important point is that yield point is not a constant, or yield strength is not a constant when we do an elastoplastic analysis. What is usually stated as an yield strength of a material is, I would say, initial yield. In fact, the stress strain curve is the locus of yield points. It's a locus of yield points. Okay, every point here after I move from the initial yield strength of the material are all yield points. Is that clear? So I can suppose I had unloaded it here, then that would be my yield point. So it's a locus of yield point that we get, okay, and so it defines the flow of the material, so called as flow curve as well. One of the other important points which I want you to remember is that this kind of nice splitting epsilon is equal to epsilon E plus epsilon P is not valid when the deformations are large. So suppose I call the strains in finite deformations, these are infinitesimal deformations. Small when I use small e or epsilon, then we are talking about infinitesimal deformations. When I talk about finite deformations, I will use capital E, and I can't use a statement or put down a statement which says this statement is not right. So though here I put this as an approximation, you will be surprised to know that in finite deformations I cannot put epsilon is equal to epsilon E plus epsilon P. Okay. To an approximation I can say delta epsilon is equal to delta epsilon E plus delta epsilon P, okay, but more correctly I would use some other notations for this. Okay, but we are not into finite deformation, we are still trying to understand small deformations. Okay, keep that in mind when we come to that state. Okay, right now let us see that I write right now delta epsilon. Okay, let me write this as delta epsilon E plus delta epsilon P. We call this, delta epsilon is what I am going to use corresponding to delta U. So it is the strain increment. Delta epsilon is the strain increment. Why I have gone from epsilon to delta epsilon? Because I am going to use an incremental iterative approach. Okay, hence I should know how to deal with delta epsilon. That's what I'll get. Right. So delta epsilon is an increment in strain, and that increment in strain can be classified into delta epsilon or can be additively decomposed. This is what the term additively decomposed into. So that means that, note this, that means that there is another way of decomposing it. We will see that there is a multiplicative decomposition later in the course, towards the end of the course, but right now I am using a very specific word, additively decomposed, okay, delta epsilon, so delta epsilon E plus delta epsilon P. My whole idea, if I have to form a tangent stiffness matrix, which is my ultimate goal, my whole idea is to do this and get what is called as the dt or et, which we did, or in other words d sigma by d epsilon. Is that clear? So d sigma by d epsilon. Now let me remove this. I hope you have understood these parts. Now let me divide this delta epsilon by d sigma or delta sigma, so that write this as delta epsilon by delta sigma is equal to delta epsilon E by delta sigma plus delta epsilon P by delta sigma. Delta epsilon E by delta sigma is what? No, what is delta epsilon E by delta sigma, or delta sigma by delta epsilon E? No, that's not at yield strength. What is delta? So delta sigma by delta epsilon E, as you write, that is the 1 by E value. Yes. So this is the 1 by E value. So the first thing that you have to notice is that E values are still valid. Okay. Obviously from this graph you will see this is epsilon E, so delta epsilon E, you can consider this as delta epsilon E. So delta epsilon E, because of the fact that I am going to unload through the elastic path, obviously the relationship between sigma and epsilon E, even in the plastic region, is through E, capital E, Okay, and so what is this E? Please note again the difference. This is my Young's modulus. This is not my strain. There's going to be slight confusions on this, but the context will tell you what we mean. Okay, this is not my finite strain. This is my Young's modulus. Please note that the slope of the unloading curve, which is E, okay, for most circumstances are the same. So this, if I unload it from here, I would be unloading it in a region or in a path which is parallel to the first one. Okay, when I unload it from here, it would be again parallel. When would it change? When I have a damage parameter that is acting. So these are again, look at the assumptions behind it. So that's why nonlinearity is very complex. Okay, a Puritan may question me. He may say that, what are you doing? There may be damage, there may be void formation, there may be other micro cracks that are formed. So in which case E may change. Okay, you go into an entirely different regime. But for most of the applications, again we abstract. So we look at the assumption. That's where our engineering judgment is there, right? We look at the significance of the problem of this assumption for that problem and say that, okay, fine, for this I am okay if I neglect the damage and E is parallel. So most of the times, okay, E is such that, or E remains a constant, or in other words the unloading curves are parallel. Is that clear? So delta epsilon E by delta sigma is 1 by E, right, plus this term. What is this term? This term is called by different names by different people. Interestingly, metallurgists are very interested in that kind of terms, delta sigma by delta epsilon P, slope of the stress plastic strain curve. Okay, they would call this as plastic modulus. Okay, many of them call this as plastic modulus and use the letter H to denote delta sigma by delta epsilon P. They would either put this as 1 by H, or some people put this as H prime as well. Okay, let's now just stick to 1 by H, okay, where H is equal to delta sigma by delta epsilon P. So note that delta sigma by delta epsilon is the what we call as tangent modulus, okay, tangent modulus, which results in that dt term. Okay, dt is a matrix. Just come to this place. Note that this dt, okay, is a matrix, and that's what we are going to derive now. And that dt has d sigma by d epsilon, okay, and from a material point of view, though this is a matrix, from a material point of view, what goes into dt is d sigma by d epsilon, okay, and let me call that as tangent modulus. Okay, this is tangent stiffness, that is tangent modulus, okay, which I call as Et. So 1 by Et is what called tangent modulus. Et. Yeah, dt is the matrix from Et. Okay, it's a matrix. Actually, B is a matrix, dt is a matrix, and B is a matrix. Okay, as a material, like you have E matrix, D matrix, and you have corresponding E to it. Okay, so E divided by 1 minus 2 nu into such and such, say for example, you would have written, right? So that's what we mean by dt, and the material property which enters into dt is what I call as Et. Okay, note again one more important thing, that unlike my good old friend E, Et may not be a constant. Okay, Et may not be a constant. That's what we're going to see now, and that this part also may not be a constant. Okay, right. So that is dictated by the curve here. If it happens to be bilinear, then I'll have only 2 values. If it is not bilinear, if the curve is a nonlinear curve expressed, for example, in terms of sigma is equal to k epsilon power n or something like that, then d sigma by d epsilon would not be the same. Is that clear? Would not be the same for the analysis. Now let us remove this reciprocal things, so that I can write this as 1 by Et is equal to E plus H divided by EH. Okay. Then let me add E squared, subtract E squared to, you'll understand why I'm doing that in a minute. Subtract, so E plus H plus E squared minus E squared, just add and subtract that, so that this can be written as E into let's just do small one more step to it. So EH plus, so that's what is the, let's look at this carefully. So EH, one second before we go further, EH 1 by ET is equal to EH divided by E plus H. Okay. So let me write this in a slightly different fashion, so that from here we will go to ET, so that it will be easier. EH divided by E plus H. Okay, I'm going to do a small manipulation, okay, with some purpose. So now let me add E squared and minus E squared. So that is equal to E divided by E plus H into H, so the first term H here, okay, plus E minus E. Okay, that's what you get. Now this can be written in a, again in a slightly modified fashion. I'm going to write it here. This can be written as E into 1 minus E divided by E plus H. Actually, I did this a small jugglery to show you one important factor. I mean, same thing, I could have retained this itself, but I just want to show you a small factor here. That's why I did that. Now note this. So as long as my E alone was there, or in other words, my body did not go to plastic strain, I did not have this term here. I had E alone. Now when my body went into the plastic region, okay, in other words, when H comes into picture, then you see that my body stiffness is going to drop by that term, right? By body stiffness is going to drop. So the one thing that has happened because of plastic strain is that the stiffness of the body keeps dropping, okay, and that is what you see as the slope of the stress strain curve, right? So we will continue with this in the next class and see how to convert or use ET in order to write down KT or the stiffness matrix. You can retain EH by E plus H itself, it doesn't matter, okay, you can do that. Anyway, I need only the ET. So in other words, the lesson is that ET is derived from E and H, okay. Even if H is not given, it does not matter in a problem. ET is just d sigma by d epsilon. If it's expressed as k into epsilon power n, you can write this as d sigma by d epsilon to be n k epsilon power n minus 1 and so on. Okay. So in other words, ET is just a function of the strain as well. Okay. So we'll see in the next class.